getting closer to doing chemistry. Every module we get closer to chemistry. Let me see, I think is it 8? Yep, module 8's when we start chemistry.
Oh gosh. A little bit under halfway there.
Mm-hmm. That's good though. Remember the analogy I made at the beginning of the year? Remember I talked about like in martial arts when you get your black belt? For underbelts, for lower belts, they think getting the black belt is when you finally arrived, like, oh, one day I'll be a black belt. Oh. And for black belts, it's like, now that you're a black belt, we can start teaching you the martial art. The white belt, yellow tip, yellow, blue, green, whatever the belting system is, that's all to get you ready to finally eventually start learning the martial art. And you start learning it when you're a black belt. So that's kind of here. You can't do module 8 without modules 1 through 7. But stoichiometry is where chemistry actually starts to happen. So, not that you're not pushing into issues of chemistry, but it's just not quite there yet. But that's cool. This is where we're at. And you guys, frankly, Mr. Parker just asked me how you guys are doing. And you guys are relatively, I mean, this is all relative, right? But to other years, I'm encouraged. You guys are doing well. You're hanging with me a lot better than some previous years. And it may not seem that way to you, right? You remember sitting there going, oh man, we're getting clobbered just like everybody else. No, trust me, you guys are doing fine. I want to encourage you not to give up. Keep pressing, making sure you understand past concepts. There may be times in when we're doing work that it brings to light that you didn't really understand something you thought you did. Maybe it wasn't tested on the module exam, so you're not quite sure that you don't know it yet. Always be willing to go back to prior things. Always be willing to go back, because when you fill in those gaps, it's amazing how it suddenly fills in that piece of knowledge that you need to understand whatever we're currently doing. Okay, so it's not a problem if, for example, you stay after on a Monday for tutoring and you want to go back to module 3 or module 2. If you need it, that's where we'll go. Because this is cumulative learning. You need module 3 to understand module 4, to understand module 5, to eventually get stoichiometry in module 8, and then we'll go from there. All right? Today is kind of that building process we're talking about, because we're moving the discussion from atoms to molecules. We've been spending most of our time speaking about the atom, the nucleus, the electrons, how to build the configurations, those kind of things. And now we're moving our discussion to the molecules, where we take 2 or more of these atoms, which are the building blocks, and we begin to construct the molecules. Okay. And we mentioned before that molecules are made up of 1 or more electrons. They're these combinations of these building blocks. And when the atoms move close to one another, hopefully now you can conceptualize the fact that when they come close together, the things that come in contact first are going to be their electrons. Those orbitals or those clouds that are around the nucleus. As a matter of fact, nucleus to nucleus contact doesn't happen. It's going to be electron to electron interaction. Now, electrons are what charge?
Positive.
Try again.
Oh, wow, there's 2.
Whoa, yeah, we'll go back to module, whatever. No. Right, so electrons are negative, and if we've got two atoms that are coming together and they're both surrounded by this negative cloud of electrons, what would you expect to happen as they come together? Like charges repel, right? We're talking about how electrons and the configurations of 2 atoms when they come together actually cause them to join together. How is it that like charges repel and yet negative coming close to negative causes a bond or a joining to take place? That's what we're going to talk about when we form these molecules and compounds. That's what we're going to be working on. So when the atoms move closer together, the first thing that are going to come in contact with each other or influence one another, it's probably a better way to put it, are going to be these electrons. And it's going to be the higher energy level, those electrons which are the furthest from the nucleus, or, again, with a quantum mechanical model, those electrons which tend to be farthest from the nucleus. Okay. Now we have a special name for those electrons, those that are the farthest away. And for this discussion on energy levels, if you need to, in your mind, go back to the Bohr model And kind of think in terms of N1, N2, N3. Remember those diagrams I showed you when electrons were excited and they would go out in energy level and then they would drop back in energy level? So if you think of a Bohr model as kind of the nucleus and concentric circles going out, it's okay if you need to think about that for a moment when it comes to this issue of highest energy level. Okay? On the highest energy level, because we know that there's actually the s orbitals and the p orbitals and the d orbitals and f orbitals. But remember, on all those different configurations, where do we get the energy level from? If we're writing out the electron configuration, how do we determine the highest energy level? Is it always the electrons that are in the configuration last? Are those always the highest energy level? No, because occasionally we have a d orbital, right? Once we start d's entering in, the d's are filling, sometimes a lower level d is filling after an upper level s. Over here, if we're filling up with a 4s, s1, 4s2, then it goes to 3d1. The 3d1, though it fills later, is not a higher energy level, it's a lower energy level. You see that? So remember, the energy level on your electron configuration comes from that first number. The number before the S, P, D, or F. That's your energy level. And that's what we're talking about here. The higher the energy level, those are the ones that tend to be the farthest away from the nucleus. And those are going to be the ones that interact with other atoms first. And we call those electrons valence electrons. So this definition is in your book. But the electrons that exist farthest from an atom's nucleus are the valence electrons. And they are the electrons with the highest energy level. The highest energy level. We've already mentioned in here that the chemistry, when we're dealing with atoms, we're dealing with chemistry, that the atom's chemistry, the individual atom, the way it behaves relative to other matter, is determined mostly by the number of valence electrons for that element. So when we look at configurations, for example, let's look here. Electron configuration for fluorine. Now, it would be a fluoride if it didn't have remember the ide names? It would be a fluoride if it didn't have the same number of electrons as protons. And that's kind of where on the test, and I'm giving you guys a couple of questions on there, or I did give you already, because in a couple cases said all atoms, for example, all atoms have the same number of protons and electrons. The way we taught it in here for that module would be, yes, that's true, because we differentiated between an atom and an ion. For the answer to the exam, they gave the technically right answer, which is no, it's not always the case because they can form ions. Well, I gave that to you because we differentiated the difference in here, okay? But looking at this configuration for fluorine, hopefully you can see now, looking at the chart, we've got the 1s block, the 2s block, so it's 1s2, 2s2. We go over to the p block, and it's the fifth one over, so 2p5. If I asked you right now, how many electrons are in the highest energy level of a fluorine atom, what would your response be? How many electrons are in the highest energy level? What is the highest energy level? 2. It's not 2p or 2s, it's simply 2. The highest energy level is the second energy level. How many electrons are in that second energy level? For this atom of fluorine, how many second level electrons does it have? 7. Correct. You see that? Does everybody see that? There are 7 electrons. There are 2 in the 2s orbital and 5 in the 2p orbital. So the second energy level has a total of 7 electrons. Let's look at chlorine. You could write out the full, I wrote out the abbreviated electron configuration. How's the electron configuration abbreviated help you? It's going to sum up, it's going to include in this bracketed noble gas all of the electrons that are in lower energy levels. That's why it makes it so easy for us. Because those lower energy levels are all summed up here, and then we just build from there. So we only have to look at a short string of maybe between 1 to 4 different orbitals that we're looking at to determine the valence electrons. Now, this electron configuration diagram for chlorine, what is chlorine's highest energy level? 3. Again, all we're looking at is the highest energy level, the highest coefficient in the front. What's the highest number? It's 1, 2, 2 on fluorine. For chlorine, all the lower energy levels are summed up in this bracketed, and I look to what's over here, what's the highest? Well, there's a 3 and a 3, so the highest is 3. How many electrons does chlorine have in its highest energy level? Again, this should be real simple. You hear a cacophony of voices, right? There's your word for your chemistry word for the day, a cacophony. And I expect Miss Bryan to use a nice chemistry term for her class. So here, we look at this and we say, okay, there are 7, because it's 5 plus 2 is 7. But wait a minute, fluorine had how many? 7. Chlorine has how many? Let's go one more. Iodine. Okay?
Also, it's 2 5s. Good one.
Okay. So iodine can be the abbreviated electron configuration. We have krypton in brackets, and then we build from there. So these are going to be higher energy level than everything that's in krypton. We see energy level 5, and energy level 4, energy level 5. So its highest energy level is the 5th energy level. How many electrons does it have in the highest energy level? 7. Good. Because there's 5 in the 5p and 2 in the 5s. Notice that all 3 of these atoms have 7 valence electrons. And this is where it gets a little bit out of order. Remember, we have to throw in the d orbitals and later the f orbitals. There's going to be a fill in there that happens that's not the highest energy level. Okay? If the 5p wasn't full, let's say a 5s2 4d10, well, that would be CD. I'm not sure, there may be cadmium, but let's say that that's what we're looking at, that if the 5 was gone, how many valence electrons are there in that?
2.
Correct, there are 2. Does everybody see that? Please make sure you see that. That if the 5p5 were not there, the valence shell, the highest energy level, would be the 4s2. Even though the 4d10 fills after that, the 5s2 is at a higher energy level. And so if the 5p5 were not there, the highest energy level would be the 5th energy level, and it would have 2 electrons. Okay? Now, those elements that fill up the d orbitals, all of these guys in here, this transition elements block, they all do some really weird things. And that weird things is due to the fact that they're filling up a lower energy level after they fill up their s block. We'll get into those in a little bit on how that affects their chemistry. Also notice that the fluorine, the chlorine, and the iodine are all located over here on the periodic table. Fluorine, chlorine, iodine. What do you notice about the pattern? They're all in the same column. That column is the 7A column. They all have 7. Okay, so boom. There it is in words for you. Atoms in the same column of the periodic table have the same number of valence electrons and have very similar chemistry and chemical behaviors. That is in your book as well, on page 134. So here's the deal. Elements in the same column all have the same number of valence electrons. As a matter of fact, the number for the A columns 1A through 7A, actually 8A, and that's an upcoming slide. I want to give you a chance to copy this, even though it is in the book. I know you're feverishly trying to copy this slide, but it is on page 134, so I'm going to move to the next slide because it builds on this idea that columns 1A through 8A, now columns 3B through right here, the section in the middle, that's kind of the wonky world, right? We're going to talk about that later. But for the A columns, 1 and 2, 3 through 8, over there, the number of the column in which the atom is located on the periodic table is equal to the number of valence electrons the atom has. That's part of the information that we didn't talk about before between metals and nonmetals. That's why it's one of the reasons why the periodic table is set up the way it is. That the column is equivalent to the number of electrons in the valence shell, the valence electrons. Okay? So what we're saying is if we were to go to the periodic table and look, for example, at column 6A, that in the chemistry, oxygen behaves a lot more like sulfur than it does with nitrogen or fluorine. Okay? The way things behave in the columns, these behave more similarly than these left, right, or diagonal directions. As a matter of fact, one of the most common hypotheses for life other than what we know as life. You ever hear the phrase carbon-based life forms? Okay, usually if you're a sci-fi person, you read stuff, you hear about carbon-based life forms. What does that mean? We talked about the CHO molecules before, and we'll get into that later with organic chemistry and things like that. Not in a lot of detail in this class, but that what we understand in terms of life is based upon a carbon basis. There's a carbon center to it. I'll just leave it at that for now. It's based on the carbon molecule. And there's a reason for that, because carbon has 4 valence electrons, which makes nice little 4 little connection points on all sides of it, which will make sense by the end of today, okay? But here's the deal. Of all the elements over here that behave like carbon, which one do you think, based on the periodic table, behaves the most like carbon? Just take a look at the periodic table. Do you see where carbon's at? Column 4A. Based on what I just told you, of all the elements in the periodic table, which one behaves the most like carbon but is not carbon?
The rest of the column?
The most. The most. Now the whole column behaves similarly, but does it make sense to you that the closer you are to the original, the closer the chemistry is? Okay? So what is the closest element to carbon that's not carbon? It is in the same column as carbon. Okay. Silicon, right? So when you watch classic sci-fi, what do they talk about? Going to other planets and finding silicon-based life forms. Why? Why did they choose silicon? They didn't just randomly pick something. What they said was, you know what? If we try to figure out life as we know it, so we need to change it in some way, but we can't conceptualize something radically different, the closest we can come up with is if we were to take every molecule that carbon-based life is formed on and replace the carbon with a silicon. Because the silicon chemically behaves the most like carbon of any other element. Okay? So that's where that thinking of silicon-based life forms come from. If I have a structure that has a carbon in it, and that's how we understand life, if I take the carbon out and I stick a silicon in, it'll be the most like life as I understand it, but not the same as life as I understand it. So that's where that idea comes from. Now, column 8A, farthest all the way on the right. I've already referred to this before, but now it's actually in the context of the class. These are known as the noble gases, also called inert gases. But noble gases is what we'll refer to them at most of the time. And we'll say that things are inert. Those aren't the only things that are inert, but they're inert gases. Do you know what the word inert means? Not the same as a nerd. It's inert. So what is an inert? If something is inert, what does it mean?
The same?
No. Inert means it doesn't react. We talked about before the air we breathe in our bodies. Most of the air we breathe is nitrogen. We breathe in the nitrogen and we breathe out the nitrogen. Our body doesn't do anything with it. It's kind of a filler. The nitrogen we breathe in and out is there so that we don't have too much oxygen, so we don't get hypoxic, so we don't hyperventilate, or so there's not too little. Nitrogen is used to balance out the amount of oxygen we need so we don't get too much. But our body, when we breathe in nitrogen, we breathe nitrogen right back out. The only time nitrogen becomes an issue for us is when we get the bends, like divers, and that's when nitrogen starts to bubble out of your blood due to a rapid decompression. And that's when you have to go into a decompression chamber, repressurize so the nitrogen can go back into solution, back into your blood, and then slowly come out rather than bubble out real quickly. But in terms of our lungs, when we breathe in and breathe out, our lungs will bring in nitrogen and we'll breathe out nitrogen because it's inert. We don't react with it. So the noble gases on the right-hand side, they are inert. They don't react. Think of it this way. God designed them so that they are exactly how they want to be, and they don't have a desire to change, right? They're already fully self-actualized, if you're a Maslowian person. They fully are happy the way they are. They don't need anybody else. They don't want anybody else. You know, they're like a lot of people today. Just leave me alone. I don't want to interact with you. I don't want to be changed by you. I don't want to be discipled by you. I just want to be left alone. Okay. Why? Because they have an ideal configuration. They have their S and P orbitals, which is their highest energy level, are full. You notice that? They are all over at the S6 level. They all have their S2s full, and now they're in their whatever Ds they may have had, but then they're over to the P block, and they're on the full side of the P. They have 6 P electrons. What does it mean for a noble gas if they take on one more electron? Think about it for a minute. If they take on one more electron, where does it have to go? Okay, their S block is full. Their P block is full. If they take another electron, where does it have to go? If we're counting up an electron configuration, I'm over here at neon, and it's a 2p6. If I have one more electron, where does it need to go? 3s1. What have I just done? I've increased the energy level by 1. I don't want to have to go to a higher energy level. All matter seeks a low energy level, right? If I've got a 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, they're all the same energy level. But if I've got to go if I've got to take one more electron, I've got to go up to 3s. Dude, I'm not doing that. That's too much work. Because I'm a high school boy. Like, nope, too much work. I'm not doing it. Okay, so these noble gases, they have their orbitals completely full. To take on any more means they got to do too much work. They're not going to do it. Oh, by the way, they don't want to give up any either, because we're going to find out that we have this thing called the octet rule, which will be the next slide. So they are right now, they have their energy level completely full. They are at a relatively low energy situation. If they take on one more electron, boom, you've just pushed them up to a higher energy level. They're not going to do that. Because of this, the chemical reactions that we're going to look at, the chemical reactions are a result of atoms trying to get to an ideal configuration. And what is the ideal configuration? It follows this octet rule. It says that most atoms strive to attain 8 valence electrons. Most want to have 8. Now there are some exceptions, like there always seems to be, right? There are some exceptions to the octet rule. The exceptions are hydrogen, lithium, and beryllium. Look over here real quickly. Notice hydrogen, lithium, and beryllium. For those, well, think of hydrogen right now. Hydrogen has 1 electron. It wants to fill that shell, right? All it has is a 1s1 electron. If it wants to fill that shell, what would be its ideal configuration? 1s2, right? It's trying to fill that shell. So it's not trying for 8, it's trying for 2. Now, let's look over here to lithium. Lithium has a 1s2, 2s1. You got to ask yourself this question. I know we're kind of personifying this, but which would be easier to do you think? For a lithium to gain 7 electrons in order to have 8, or to lose 1 in order to have 2 and have its 1s shell full? The answer there is it's easier to lose 1 than it is to gain 7. And the same thing with beryllium. It has a 1s2, 2s2. Okay? The first energy level is full. The second energy level, in order to fill that, I've got to pick up 6 more electrons. It's easier for me to shed 2 than it is for me to gain 6. So that's one way to think about that. Hydrogen wants to gain 1 to have 2, like helium. Lithium and beryllium want to lose electrons to have 2, like helium. After that, everybody's trying to get 8. Okay. So, the octet rule. That's why it says most atoms. You will always get a question that says the octet rule says that every element wants, and your answer to that is no. The octet rule does not say every element wants to have 8. The octet rule says most elements want to have 8. And the hydrogen, lithium, and beryllium are the 3 exceptions. Okay, so I've already given you the test question for that. Okay, because people will eventually say, no, the octet rule says every one of them wants to have 8. Virtually every one of them wants 8. You always have a couple exceptions. Hydrogen, lithium, beryllium are your 3 exceptions. Hydrogen's already set, or excuse me, helium's already set, and those other 3 want to be like helium. After that, yes, every other element wants to have 8 in its valence shell, its valence electrons. Okay, we get to move on to the second section, Lewis structures. I love Lewis structures. Lewis structures are cool because now we start to kind of visualize, in a way, this is a model, okay? The Lewis structures are a way of modeling the valence electrons. But guess what? We're not going to do it with s orbitals and p orbitals, and we're not going to do a 3-dimensional visualization. We're going to start by doing a 2-dimensional visualization. Don't worry, we will do a 3-dimensional visualization later. Not this module. We're sticking with for 2. Later on, I might refer to it as a 3-dimensional Lewis structure. Right now, we're doing 2-dimensional Lewis structures. So a Lewis structure, sometimes called an electron dot diagram. I might say electron dot structure, might use some. I would really prefer to just always call them Lewis structures. Now, why do you think scientists, and chemists in particular, prefer to call them Lewis structures instead of electron dot diagrams? There's a good reason. It makes perfect sense. An electron dot diagram is what it's going to look like. You're going to look at the symbols, it's going to have dots around it, and you're going to think electron dots. Okay, but we prefer to call it Lewis structures. Because, why do you think a Crookes tube is called a Crookes tube?
Because Lewis just made / discovered whatever it is.
Okay, I can almost decipher what you meant. Try again.
Lewis made.
Okay, so you've gone from Crookes back to I asked about Crookes, now you're going back to what I said about Lewis. Okay, go ahead.
Lewis made the structure.
Lewis came up with this method, right?
Yeah.
That's why Crookes tube is called a Crookes tube, because Crookes came up with it. That's why America is called America, because of Amerigo Vespucci, right? We don't call ourselves the United States of Columbus. We call ourselves the United States of America because of Amerigo Vespucci, right? Why do we call ourselves America? To honor Amerigo Vespucci. Does anybody want to tell me about Amerigo Vespucci? Why don't we call ourselves the United States of Columbus? Columbus was here in 1492. Vespucci didn't make his trip until 1501. So why are we the United States of Amerigo? Amerigo Vespucci. He's an Italian guy, so I don't speak Italian, but it's fun to say it that way. Amerigo Vespucci. Because Vespucci was the one who figured out that North and South America were not Asia. Columbus still thought he was on the eastern side of Asia. Vespucci said no. What Columbus discovered is actually a land between Europe and Asia. So we are the United States of Amerigo Vespucci. This is the Lewis structure because Lewis came up with it. And if you want to completely rip him out of the history books and not give him any credit, you can call it an electron dot diagram, which I do occasionally, just like I sometimes say atomic weight. It's wrong, technically, Lewis structures. So what is it? You don't really care about Amerigo Vespucci. You care about what in the world is a Lewis structure. Okay, here's how we start. Lewis structures, aka electron dot diagrams, start with the atomic symbol in the center. You write the atomic symbol for whatever it is. In this case, guess what this is? This is a Lewis structure for lithium. Good. So you start with the chemical symbol, and then you place 1 dot for every electron in the valence orbital, the valence shell electrons. Lithium has 1 valence electron. How do I know that? Well, come over here. Lithium is in the column 1A. So an S1 is its highest, the s orbital of that energy level, the second energy level, 1 electron in that energy level. Does that make sense to you now? Okay, so that's where I show my 1. let's go ahead and count this up a little bit. If we start on the second energy level, we're at lithium. If I go to beryllium, what do you expect to find? Boom, 2. Okay? So beryllium has 2 valence electrons. Lithium had 1. There's a pattern forming here. Did you see? Notice where the first dot was? Okay, where's the second dot? Beryllium puts it there. What's the next element on the second energy level, Phil? Boron. It has 3. Where do you think that third dot's going to go? Boom! There we go. Okay. The $6 million question. Next element. Carbon. How many valence electrons? Where is that last dot going to go?
Oh.
Okay. Now it's actually now it's going to get tricky, right? Because what's next? Nitrogen. Nitrogen is in column 5A, which means it has 5 valence electrons. What do you think?
I think it's going to go right back to the right.
Ooh.
Okay. And then guess what the pattern is from there? We just keep going around. So when you've got 1 electron, 1, 2, 3, and 4, they're all centered. When you have 2, as you build it up, you offset them so that they are beside each other. There's oxygen, fluorine, and neon. I should make a little movie. See how it goes forward. Ready? You start at the 3 o'clock position. You had 1 dot, 1, 2, 3, 4, offset 5, offset 6, offset 7, offset 8. And you get to the place eventually where, for example, if I said, draw the electron structure for fluorine, you would look over and go, fluorine. Fluorine is in column 7A. Fluorine has 7 valence electrons. That means I've got doubles except for the 1. The one that's not a double is the top. Boom, put it in the center. Then pair, pair, pair. Okay? So you start to figure that out. If you have 5, you have a pair on the right. If you have 6, you have a pair on the right and on the bottom. You have 7, you have a pair on the right, the bottom, and the left. You have 8 pairs all the way around. Now, if we were to go back, okay, I get to use the back button again. Let me go back. Let's pretend, I haven't done this, let's pretend rather than lithium, I plug in sodium. Okay? If that were sodium, guess what the Lewis structure would look like?
Just 1 dot.
The same as this. It would just have Na with 1 dot. Next would be magnesium. Guess what magnesium looked like? It would look just like beryllium, except they would have Mg in the middle. And then we go to aluminum. Aluminum is a column 3. Guess what it would have? Boom. But it would be Al. And then after aluminum, silicon. Just like carbon, but instead of a C, we would have Si. Phosphorus, just like that, except rather than an N, it would be a P. Sulfur, or excuse me, sulfur. Sulfur is column 6A. Just have an S rather than an O. Chlorine, 7. 7 would have a Cl rather than an F. And then argon has 8, but rather than Ne, it would be Ar. So you see the pattern follows in the column. If you can do the Lewis structure for any element, you can do it for every element in that column. Columns 1A through 8A, not including transitions. Those are a little different. All right? Any questions on drawing Lewis structures then? Because we have, on your own, for 1, we're going to take just a couple minutes and do that. We can do it together. It's really simple now that we understand it. We can do it with our eyes closed. Maybe peeking to find out the column, but other than that, okay. Lewis structure for calcium. Okay, do you see that you don't really care the energy level? You don't really care what came before. You're looking at its the highest energy level. You look over here at calcium. Where is calcium at? It's a column 2A element in the 4th energy level, right? So its valence electrons are what? What are the valence electrons? Let's go back to something that's actually a little harder. What are the valence electrons for calcium? They're the 4s1 and 4s2, right? Do you see that? Does anybody not see that calcium's highest energy electrons are the 4s1 and the 4s2 electrons? Okay. With nobody saying they don't get it, I'll assume you do get it. So there are 2 electrons in the highest energy level for calcium. So what would the structure look like? We would have dots where?
To the right and to the bottom.
Okay, so in my class you would say at the 3 o'clock and 6 o'clock positions. Okay? Right there. At the 3 and 6. Guess what this side is over here?
9,
And up is?
12.
Yeah, because 0 position doesn't make sense. Okay.
0.
Silicon. It's in a column 4A element, 3rd energy level. You've got 3s1, 3s2, 3p1, 3p2. You could do that and say, hey, the 3rd energy level has 4. Or you could say, I'm smarter than that. I know that's a column 4A element, therefore it has 4. I have to account for 4. Where are they going to go? They're going to build up on all the cardinal positions. Being able to do a Lewis structure for an element is going to become critically important when we start doing compounds, which is tomorrow, okay? So being able to draw a Lewis structure for 2 different atoms will help you be able to visualize how they're going to come together to form a molecule. Okay, this part is simple. Tomorrow, and that's why we're not going to push into it today. We're going to start it tomorrow. But we start applying this for 2 different structures that come side by side each other. One last on your own, astatine. Who's found it? Okay, where's it at? Column 7A, all the way at the bottom, right? So you could count it up, you could do the abbreviated electron configuration, or you could just say, how many valence electrons does it have? 7. Why? It's in column 7A. So I have to account for 7. Hopefully you see now that it's going to be pairs everywhere except for 1, except for the top. There's my 7. That's the Lewis structure for astatine. Okay? Now on example 4.1, I didn't do that one, but you can look at it as well. It's simple as well. It's on page 136. They asked for the electron configuration, the Lewis structure for sodium. Sodium's highest energy level electron is, hopefully you can see right now, it's in the 3s1 position. How many do I have to count for? 1. Where's it going to go? The 3 o'clock position. Element here, name escapes me, but symbol is Ga. You find it on the periodic table. You run up and say, hey, that's a column 3A element. How many valence electrons does it have? 3, because it's in 3A. Where do I place them? 3, 6, and 9. Okay. And last one here, element is Te. Te. Not Te, it's Te. Okay. Over here, column 6, it's in the 5th energy level. So column 6, 5th energy level. Column 6A, which means it has 6 electrons. And it would have the same structure as what we showed oxygen before. 6 is 2, 2, 1, and 1. All right? Now, this isn't really part of this module in the sense of it's not taught in here, but think about this. If we are counting for 8 electrons, do you recognize that what we're showing on these are the s and p orbitals, each of which can contain 2 electrons each, right? You've got 2 electrons in the s orbitals, and you have 2 for each p orbital, and every energy level has 3 p orbitals for a total of 8 electrons. Which is why we show them in pairs. We can visualize them in pairs this way. And we're basically recognizing that, hey, you know what? In one of those orbitals, I have a p orbital that could hold 2, but it's only holding 1 right now. So what do you think I'm going to do? We're going to start talking about reactions between. And we've already mentioned before about metals and nonmetals, right? Remember we talked about metals and nonmetals? And we said, what were the characteristics between metals and nonmetals? Metals want to do what? Right. Well, those are the physical attributes. We talk chemistry. What do metals want to do? Didn't we talk about how they want to become positive? How they want to give away electrons? Okay? We'll get into that tomorrow then, if you don't remember that, because I taught it as like an additional, oh, by the way, this is going to become important. Now, this is going to become important like tomorrow, okay? If I have something up here, which obviously there's 7 electrons, it's trying to get to 8. It needs 1. It wants 1. Okay? If it wants 1, it's behaving like a nonmetal, because nonmetals want to take electrons. Metals, they want to give up electrons, right? Remember I said over here for like lithium? It's easier for lithium to give up 1 than it is for it to gain 7. And that's where we're going to start finding out the characteristics of metals and nonmetals and how they form different compounds. If I have a nonmetal that wants to gain an electron, and I have a metal that wants to give up an electron, guess what? Perfect union. You know? One wants to get rid of, we can strike a deal. Striking that deal is chemistry. Well, part of the language of chemistry. Like I said, chapter 8, stoichiometry, is chemistry. But we're not going to understand chapter 8 until we understand how compounds are formed. Compounds form because of the reaction between atoms, and that is the movement of electrons, either between atoms or the sharing of electrons between atoms. Tomorrow we're going to start talking about ionic compounds. And ionic compounds are when a metal and a nonmetal work out an arrangement. A metal who wants to give up electrons meets a nonmetal who wants to take electrons, and they strike a deal. And they form a compound. After that, we're going to learn something a little more complicated, and that is when 2 atoms that come together that both want to get electrons strike a deal and they share. There is no such thing as 2 metals forming a compound because they're both trying to get rid of electrons. Neither one of them wants to take them. Because they're both trying to get rid of and not take, they won't react with one another. A giver and a taker can form a team. A taker and a taker can share. But a giver and a giver, they can't work it out because nobody's willing to take. Okay? And that right there is kind of a summary of reactions. That everything can be understood in terms of if you get 2 people together, they're both trying to get rid of something. Like a game of pit. Ever play games like that where you're trying to give away cards or trying to get cards? If you're trying to give something away and the other person's trying to give the same thing away, you can't work a deal. But if you're trying to give something away and the other person needs what you want, they'll take it. It's chemistry. Any questions then on Lewis structures, 2-dimensional Lewis structures? So you should be able to find an element on the periodic table, and if it's in column 1A through 8A, be able to determine how many valence electrons it has, and then be able to draw the Lewis structure for it. And the Lewis structure, again, is just simply the chemical symbol for that element and the appropriate number of dots around it, filling from the 3 o'clock position around until you've placed them all. Dots are centered when there's 1, they're moved offset and paired when they're 2.